Hello, ladies and gentlemen. This is Dean from Pi, and this is Linear Algebra. Today, we're going to look at some operations you can apply between matrices. Matrix addition is incredibly simple and almost identical to vector addition. You just add the corresponding entry, which is to say with the same coordinates. Transposition is also simple. This simply swaps the column and row spaces of a matrix, or column and row vectors, that is. Changing the rows into columns and the columns into rows. This is denoted a to the t. Multiplication, however, is a bit more difficult. The first thing you do when multiplying matrices is identify the sizes. Matrix multiplication is very touchy and specific because it involves dot product, which can be called inner product as well. And therefore, the number of rows in the first matrix needs to be equal to the number of columns in the second. If we multiply a and b, the sizes need to be in order, aj by k and bk by l. And then therefore AB will have j by l size. This means that the order that the matrices are put in the equation does matter. A good way to think about this visually is if the middle are equal, and then you take the outsides of those. Now that you've found the size, the entry ij of AB is the dot product of the ith row of A and the jth column of B. That means that you have to take quite a few dot products. As an example, let's take 4,8,3251 multiplied by the vector 4, 2. And you can actually see this 4, 2 as a matrix because vectors are technically just n by 1 matrices. Since these are 3 by 2 and 2 by 1, the product will be 3 by 1. And the entries are going to be the dot products of these, which are 4 times 4 plus 8 times 2, 3 times 4 plus 2 times 2, and 5 times 4 plus 1 times 2. Or, to simplify that, it's 32, 16, 22. Remember when we talked about special matrices, we said that some have certain properties when multiplied by. The most important is the identity matrix, I, which is like 1 in the sense of multiplying because AI or IA is just A. And the row operations matrices apply their operation when multiplied, but only when they're first in the order. If they are second in the order, then it's column operations, not rows. The last operation, inversion, can involve determinants, but not always. So if you haven't watched the last video, go back and check that out after. We use inverse matrices instead of division because you cannot do something like divide a scalar by a matrix. Therefore, putting a to the power -1 is used instead. And unlike algebra and calculus, a to the -1 is not 1 over a for that same reason. In general, to find an inverse matrix, set up the matrix A with the augment I, the identity matrix. Now, when we reduce A into reduced row echelon, the augment will turn out to be A inverse. Multiplying A by A inverse or A inverse by A gives you the identity matrix, which means that this method is sort of like matrix division in a way. In the event that A cannot be reduced, it's considered singular or uninvertible, and the determinant will be found to be 0. Therefore, if asked to find if a matrix is invertible, all you have to do is show that a determinant is not 0. As a shortcut, you can find that all 2 by 2 matrices inverses can be found if A is A, B, C, D, then A inverse is 1 over the determinant of A times D, -B, -C, A. And here you can see a bit more clearly that the determinant can't be 0 because then you'd be dividing by 0. The general method of finding inverse matrices can be extended as well, and it can be proven that two arbitrary matrices A and C, where A is non-singular or invertible, A augment C is reduced into A prime augment A inverse C. which is technically what we did because A inverse is actually equal to A inverse times I.